Hi, this is Dr. Huckabee. This is an edited lecture from last semester. It was the second lecture that I gave in the spring of 2020, and it was modified slightly for our uses here. It covers from chapters 1.1 to 1.10 and covers a lot of review material for you. So please make sure that you listen to this and do the play posit. In addition, I'd like to bring your attention to your first to-do list, which is to visit Canvas, review the syllabus, the Gen Chem material. Make sure you get on Gradescope because this is how we're going to do homeworks. Begin reading chapter 1 so that this lecture makes sense, and contact me if you have any academic conflicts or anything regarding the letters of accommodation for the DRC. Enjoy. Okay, so welcome everybody to the second lecture. I'm glad to have you all here. It seems like enrollment was more or less what we had before, so it seems like I wasn't the absolute worst last time. So up here you can see a couple of things to think about. The fact that maybe plastic dinosaurs are actually dinosaurs, and a more scientific thing to do with water and ethanol, because again, with the reasoning of analogy, thinking about what makes certain functional groups similar is very important in organic chemistry, because they both also share something in common with what we call cetyl alcohol, which seems very different, right? It has so many carbons and hydrogens, and yet all three of these things that I showed you have both an alcohol functional group here. And a functional group is what we're going to use when we talk about several properties of molecules, because functional groups are really what makes molecules act like each other. If you can understand functional groups, you can understand organic chemistry, because more or less organic chemistry is the study of functional groups on organic molecules. I would like to first ask a practice question, one that's going to kind of be a theme for today. Maybe not a theme, but it'll get you thinking the right way. I had the answer up there. That's smooth. So the question is, what shape do you think each will have? For CH4, for the methyl anion, and for the methyl cation. Give you a couple minutes to think about that. Maybe you can ask your neighbor. Maybe you can talk about something you did this weekend instead of any of this. That's fine. All right, so A. A we talked about before. A is the simplest organic molecule. A has what type of geometry? Anybody? Just yell it out. Tetrahedral. I saw some people say it. Okay, good. CH4 is tetrahedral. Tetrahedral. Exactly. I think maybe I have a drawing. Oh, look at that. Tetrahedral. Okay, what about the methyl anion? So one of the hydrogens is gone. Instead, you have a lone pair. What geometry do you think that will be? Anybody? Okay, tetrahedral. I heard it again. Very nice. Tetrahedral, exactly. Now, last, what about the methyl cation? There's no lone pair. There's no hydrogen. Anybody? Maybe you just saw it. It's going to be there's going to be planar, trigonal planar, because while you would have a space for extra electrons or an extra hydrogen or something, there's not one. And so the molecule as a whole would be much happier in this trigonal planar arrangement. So we're going to think about the structure that I drew here, actually, and because we're going to talk a little bit about hybridization, because this is kind of a key element, especially when we're thinking about why representations are important in molecules. So let's start with this CH4 molecule, and let's talk about why it has the hybridization and the structure we see here. And so to do that, let's start with a very simple representation of carbon. So carbon has the atomic number of 6, right? And its electron configuration is 1s2, 2s2, 2p2. And we said last week, as I was going through very quickly, that you can write out the electron configuration more succinctly like this, where you have energy increasing as you go up, and you draw the 1s, 2s, and 2p orbitals, like so. And using your electron accounting rules, we can draw the electrons in this way. So this electron configuration that I've drawn is the theoretical representation of the Lewis dot structure that I've drawn here. Right? You have two p electrons by themselves, and you have two s electrons on top. Now, you probably see the problem with this already, and that's the Lewis dot structure carbon is way different than the tetrahedral carbon, because we know carbon needs to make 4 bonds. So because we kind of already know the conclusion of this story, it helps us to think about why we need to hybridize. Because if you just made C, H, H, with 2 electrons there, there's no way this is actually a material you can measure or that you can study. Because this carbon, while technically neutral, does not fulfill its octet rule. It has 6 valence electrons in total. It will react with anything. Probably even oxygen from the air, nitrogen, whatever you try to put this in, it will be gone. So the way that nature deals with this is that instead of having 6 electrons, what it will do is it will promote one of these electrons up into the higher energy orbital, and in doing so actually causes stabilization of all 4 at the same time. So maybe 1 electron is promoted in energy, and that's less good, but overall, whenever we draw them underneath, you will see that the energy of the other 3 comes down enough to balance that out and even make it an energy gain. So the system really prefers to have less energy, and so the molecule is very happy to do that. So let me redraw that electron configuration now. So you have energy increasing as you go up. You have your 1s orbital again. We'll just go ahead and fill that in because we know it's there. But now you have 4 orbitals with 1, 2, 1, 2, 3, 4. 3, 4. Do you understand why I drew that last one pointing down? Because I'm trying to show where it came from on the other side. Because we kind of borrowed it from the other 2s orbital there. Now, in doing this, this is kind of a hand-wavy thing to say, like, what does this mean about the orbital? What this means is that we took 2 orbitals, the 1s, that looks like a circle, right? And we took a p orbital that has an oblong structure, like this, and we mixed them together. So now every orbital in this electron series here is going to have those same properties. And what those properties are is that essentially you are going to have one side with constructive interference, it gets bigger, and one side with destructive interference, it gets smaller. So the overall sp orbital we're going to generate, or sp3 orbital, is going to look like this. One very big side because you have constructive interference from the s, one very little side because you have destructive interference from the s. Does that make sense? It's like when you have a really hard decision to make. Sometimes you get a really nice thing that comes out of it, but you still have to deal with something bad that maybe you didn't foresee. Same idea. And what this means for a molecule is that mostly you get something good, because here you now have those 4 valence electrons that are available, right? That's what we already know carbon likes to do. And from here, it's fairly straightforward to add 4 hydrogens. Let's do red. And then join them together with these sp3 orbitals. Right? And so because these orbitals are so large, you can only arrange them in very specific ways, and they can only come so close together. And here that is 109.5 from each, and that together makes a tetrahedral structure, just like we have drawn here. And you might notice that this representation of CH4 is much different than anything we've seen so far. And this is actually how organic chemists like to look at carbon, each carbon atom. It's called a wedge and dash structure. And if you look, we have 2 lines that look like they're more or less just regular lines, right? But then we have 2 lines that look special. One of them is a wedge. You know, it's much thicker. It's what I guess it's like bold, right? And the other is the dash. And that's trying to show you one hydrogen coming out at you and the other going away. You could imagine that the other 2 are here, and those other 2 hydrogens are pointing really out or away from you. So using this, you can kind of see a little better what the tetrahedral structure of a carbon really means. You know, it's not 4 lines on a paper and it doesn't matter where they are. Sometimes what is bound to the carbon in the exact placement of that atom really matters, especially when you think about medicines and really functional molecules. Now, so far we've just talked about methane. And methane, while it's really good to burn and get energy for, isn't so exciting. So what does this actually look like whenever we put 2 carbons together and make more complex structures? So we can start thinking about more complicated structures simply by putting 2 carbons next to each other. Right? So there are 2 valence atoms, and each has another set around it. So we'll give each the bond with each other, and throw some hydrogens around it, like this, and put in some electrons for each hydrogen, and connect them as well. But you know, hydrogen is actually an s electron or s orbital, right? So maybe it should look spherical. And these are the sp3 orbitals here. But you all are already professionals in organic chemistry, so you already know all this. You know that hydrogens bond through spherical pathways like you see, or through s orbital mixing, as you see up here, for C2H6. So that's not something you really need to explain, or I need to explain to you, because you've already seen that from your book, right? But what if we go a little farther, and instead of talking about C2H6, we now look at a case where you have C2H4, as I have drawn here, right? Because I haven't put anything on those top 2 p orbitals. What would happen if there just wasn't a hydrogen there? In that case, now we could actually go back and look again at the electron configuration and find out what that would do to the geometry of this molecule. Because now, instead of having four valence electrons that you need to use, like with methane here, now you only have 3 for each carbon atom. So why don't we go to a new sheet, and we'll make another electron configuration, just like we did before. These are really useful. 1s, 2s, and then we'll do the 2p again. Because remember, before we mixed all 4 together. So this time, since we're only mixing 3, we need to go back to the very beginning, which is carbon's atomic electron configuration. So we'll give it its electrons, 1, 2, 1, 2, here. Okay. Now, if we go ahead and say that we only need 3 here, these 3, then when we mix all 3 atoms together, and again, energy is always increasing as you go up. You have the 1s, and you have the now mixed set of 3, or yeah, I guess really we should have already assumed this was up here, right? That would make more sense. So we already assumed they're already mixed, but not totally put into the sp3 yet. So they can be, but we only selected 3 of those orbitals here. Then we could make a series of 3 new orbitals, because since we had 3 in, we have to have 3 out. And we have 1 orbital left over, which will go on the top there. So we'll call this, instead of sp3, we'll call that sp2. And we'll still have a p orbital that's still at the same energy level. So here you can really see, by hybridizing, you bring the energy level of the overall 3 orbitals down. And from there, you're then left with the same 1s that we don't worry about, each of these, and you still have 1 in the p orbital. So now you can see that whenever we draw a structure like C2H4, so I'm going to draw it, I'm going to try to draw it in a way that preserves 3D structure of it. So it might work, it might not, but you'll just notice that I'm trying to draw everything in the plane of the paper. Okay. So here, if you have the carbon, and it's bound to the carbon like this through each valence electron, and we have another hydrogen coming out like this because it has a valence electron. Hydrogen has one, and they're bound together. We'll do the same on the other side. Again, the hydrogen's valence electron there. We'll try to put the hydrogen out like that. So hopefully you can see that I'm trying to make it the same plane, but I'm not the best artist, so hopefully you can bear with me there. There we are. Okay, so now each hydrogen has its own valence electron. It contributes as well. But the p electrons are still sitting up here, right? So now when we hybridize those, there's not actually a hybrid on top. Those are just p orbitals. So we can't draw them with that funny shaped lobe like we see on the screen, right? We have to draw them like a regular pi orbital. Two lobes, the same size, regular p orbital. And does anybody remember why I made them the same colors on top and bottom? Anybody? Just because I didn't care, I threw it together? No, I put them the same color because you have to have constructive interference, as we remember from valence bond theory. Constructive interference means you make a bond across each, and there's an overlap, right? But you can also have a molecular orbital theory explanation for why this works. Because we kind of waved our hands over here and said, we mixed these things together and we made 3, and now there's a p orbital that can bond with each other. But molecular orbital theory actually gives us a really nice way to think about this. Because in molecular orbital theory, we can draw a new diagram that helps explain it. So again, energy always going up. We're going to mix 2 p orbitals as we just did. So here's our 2p and our other 2p. And they come together. They're close enough to interact. Now, I drew them up and down because, again, we want constructive interference for any bonding to happen. So we're going to make one at lower energy, but the trade-off is we're going to make one energy level at higher energy. And then we'll fill this. So now we have a p-p bond, or pi bonding, a pi bond, if you will. And each of these actually has a structure because, again, remember we're talking about constructive, destructive interference. The highest occupied molecular orbital, the one with constructive interference, the one that matters the most for reactivity based on electrons, or based on this molecule's electrons, looks like this, where you have both phases of the pi orbital on the same side of the carbons. Both nodes, there are no nodes essentially because you have overlap. But the non-bonding form, where you don't have overlap, looks different, right? The lowest occupied molecular orbital has a different structure. And that is with opposite phases. And those opposite phases tell you that there is no bonding there, because that means that you cannot have overlap between them that is constructive. This is a destructive interference here. That's why it's higher energy. One second. Okay. Yes. Exactly. So, the difference between the angles of the CH bonds between this and the tetrahedral is that the alkene, the double bonded two carbons here, have a difference, an angle between the two hydrogens of around 120, and the same for the carbon and the hydrogen, around 120. And that's because around the whole carbon, you're distributing those atoms around 360 degrees. So you're going to keep 120 in between all of them. Now, this example we talked about for alkenes is actually the same for alkynes, the molecules that have 3 bonds. Alkynes have a structure like this. We'll learn about them more in Chapter 4. But you'll notice that it's another type of carbon-carbon interaction. And in this type, you actually only have 2 bonds that look like they could be hybridized, as we saw before with C2H6. So if you, again, go back, we can go through this one a little faster just because we've already done 2 of them. And you have, again, the 1s, the 2s, and the 2p orbitals. They're all ready to hybridize. This time, we only want to select 2, right? Because we have only the 2 interactions that we're talking about. Does that make sense? Okay. So since we only have 2, we're going to make another electron configuration. Missed that one. With the 1s, as always, and then sp with 2 pi orbitals. Okay, so we have these guys here and these guys up here now. So you see we have the electrons from the CH and the CC here that are the sp bonds. So that's the hybridization we have now. But now we have 2 pi orbitals, and it turns out that if you look at the, sorry, if you still need that, I can put it on. Am I still ready? Yeah. If you look at the same type of molecular orbital theory assignment, again, with energy increasing, and you mix 2 p orbitals here, up, up, and down, down. Instead of mixing and getting 1 of each, you're going to mix and get 2 of each, actually. Because, if you'll notice, we had 4 that we went in to our big blender, if you will, and then 4 had to also come out. Okay, so when we do this, we then put them in the orbitals, as we always do, and you'll notice that we filled up the bottom energy levels, but we didn't touch the top energy level. So again, we have an energy level that is the highest occupied molecular orbital. and we have a lowest unoccupied molecular orbital. And they're going to look something like this. Each one is going to be the same as we saw before, except for what? We have one here, right? We have, I'm showing you one HOMO, one LUMO, but you saw before already in this example that the triple bond has 2 pi bonds. So where do we put those? Well, we put them, if you could imagine that, you know, my arms here are the carbon-carbon bond. You're going to have one p orbital that is straight up, and you're going to have one p orbital that's straight out this way. And the other 2 hydrogens are going to also be straight out this way. So if you look at the simple geometry of the molecule, it will again be this. That's a line, right? So the geometry of the molecule will be linear if you look at it this way. But if you draw in the pi bonds, like we did before for C2H4, the alkene, you'll notice something a little different. So here's the carbon bonded to the carbon, and it also has a hydrogen. I'm leaving out the sp mixing, that way we can draw the p orbitals better. So now you have 2 p orbitals, one here. Okay, now you're all really going to have to bear with me because this one is the hardest one, I think, to draw. Then you have, like, p orbital that comes out this way. It's out this way as well. Here, so you see that you have mixing across and mixing down, and then you have mixing on top and here in front. So you see that if you look at now the electrons in addition to the atoms, you don't just have linear, or it's not just a line, right? Now you can actually imagine that you can draw a plane 2 different ways. You can draw a plane that encompasses kind of like this, where you have kind of a triangle across. I don't know if you can see that very well. It gets a little complicated. And you have another one here that is like a triangle across, right? So it's kind of like if you take into account the electron clouds, you have a different geometry than if you take into account simply the atoms. Okay, now in alkynes, especially C2H2, it doesn't actually help you very much because since you have 2 planes, they actually cancel each other out. But that gets us to the really more important idea in organic chemistry, and that is this idea of a difference in atomic geometry, or sorry, molecular geometry, and geometry where you incorporate the lone pairs as well, or what you might remember as valence shell electron pair repulsion. Because this NH3 group has trigonal pyramidal geometry if you just look at the molecule. But it has tetrahedral geometry if you actually look at the overall, how do they draw that? Yeah, if you look at the overall structure here, right? So there is a difference there, and that actually will cause a difference in the organic chemistry that you see occurring. One quick thing before we move on to geometry and the VSEPR rules. I mentioned last week quickly that you had a difference in bond strengths from alkanes here to alkenes here to alkynes. So and you kind of think of that as you have a much thicker bond. You know, if you've ever played tug of war with a dog, you know, and you have like one piece of rope and it's, you know, not very fun for the dog because there's too much tension, but then you start increasing the tension of the rope, and now it's like you're bonded together much more and you can really tug each other. It's a lot stronger, right? The same idea for these extra bonds you're adding. The energy of stabilization increases because the bond is more stable. So if you have the alkane, you have 368 kilojoules per mole. If you have an alkene, it's 632, and if you have the alkyne, it is 820. So you can see a huge difference in stability between all three of them. As you add pi electrons, you really make a much more stable, much, some people like to say, happier molecule. It is very difficult to totally destroy an alkyne.